Good evening, all of you. Am I audible?
Yeah, I can hear you.
Okay.
Yes, sir. So you're audible, sir.
Mhm. Good evening and welcome all of you in SOAWAL-CSE 2 webinar 8. Uh, and welcome Professor Saugat Bhattacharya. So before starting the webinar, I just want to play one introductory video for the university. So it will take just 5 minutes. Let me share my screen first. Just a minute.
Gaurav, sir.
Yes, ma'am.
Actually, it's raining so heavily. I don't know,
Mhm.
like everybody's stuck here. It's raining so heavily out here. Saugat, sir, very good evening. I think it's morning out there. It's
Yeah,
raining so
it's afternoon
badly
here.
here
Yeah.
that so okay, it's afternoon. So it's raining so badly here. I think that's why the attendance is so low. It's like so bad weather over here. We have asked students to join. I see they're joining, but Gaurav, sir, are you able to play the video?
No, actually, I am facing some issues for sharing this video.
Internet. Okay.
Yeah, I'll
Okay,
stop
so let's
presenting. Maybe you then it can you can run the
start
video then.
talk first. Then, if I able to play the video, then I will play it.
Okay, sir.
Okay, so welcome again, Professor Saugat Bhattacharya, and let me introduce him. And I am Dr. Rourab Pal from CSE SOA University, and Saugat Bhattacharya is a lecturer in computer science in the School of Computing, Engineering and Intelligent System, Ulster University, Northern Ireland. He has got his doctorate from Jadavpur University, India. He was Senior Research Officer, University Essex, England from July 2017 to April 2020. He was postdoctoral researcher in INRIA Sofia Antipolis, Mediterranean from November 2015 to July 2017. He was visiting scientist in Paul Valery University of Montpellier from October 2014 to June 2015. His research interests are brain-computer interfacing, cognitive neuroscience, artificial intelligence, and machine learning, and its application in human-machine interaction and neurorehabilitation. His research is primarily focused on developing brain-computer interfacing system based on robust signal processing, quantitative and machine learning algorithm to draw interference into an user state of mind through their neural and other psychological signal. He has over 60 publications in form of peer-reviewed journals, international conference, and book chapters. He is a recipient of US Ireland R&D Partnership Program, Center to Center Mechanism, and GCRF palm priming as a co-investigator and 2 PhD fellowship by CSIR India and Erasmus Mundus fellowship. He is also an associate editor, board member in Frontiers in Medical Technology and MDPI Brain Science, and served as a guest editor in Frontiers in Neuroscience, MDPI Sensor and International Conference on Intelligent Robot and System. Okay. So, Dr. Bhattacharya, yeah, please start your presentation. Over to you.
Okay, thank you, Rourab. So hello everyone. Good evening, good afternoon. So this is today I'm going to talk about one of my researches, one of my research strand that is applying brain-computer interfacing on group-based decision making. So hence the title, Collaborative Brain-Computer Interfacing for Augmentation of Group Cognition. So I'll start off the talk with a brief introduction on what actually brain-computer interfacing is, and then we'll get into what decision making is, what I mean by decision making, and then what group cognition or group decision making is, and how the brain-computer interfacing can improve our group decision making capability. So as Dr. Rorav has rightly pointed out, that I am an assistant professor or as lecturer here in the School of Computing, Engineering and Intelligent Systems. So starting off, the first question that we might ask ourselves is, what is brain-computer interfacing? So when brain-computer interfacing started out, it was simply defined as a communication system that does not depend on the peripheral nerves and muscles. And basically, this was technology which would allow a human being to control a computer or any peripheral devices or any robotic devices just using their thought, or basically, as we say it, brain signals. But now brain-computer interfacing has expanded a lot. Now, other than developing as a communication system, we can also use it as a monitoring system for our different states of arousal or different states of fatigue or different states of stress, anxiety, monitoring different levels of other cognitive states like uh, workload management and so on. So as you can see from the small GIF file, that when the brain-computer interfacing started out, then the researchers or early researchers, they used to just record the signals from the brain and then use a computer or some other device bring to gather meaning from that signal. I'll come to that in a bit, but gather meaning means that develop control commands, or at that time it was mostly about developing control commands and then send it over to a computer in this case, where it was used to control, say, a mouse. So a brief idea on actually what happens behind the wheels, or you can say a more low-level understanding of what I mean by brain signals. So how do we translate, or what do we use, what principles do we use to translate our thoughts into actions? So I hope most of you know, but if you don't know that, but our brains is full of neurons. It's the like billions of neurons. The billions of neurons make up our brain, and each of these neurons are connected to each other by axons and dendrites. So these neurons connect with each other to form a superhighway for nerve impulses, and basically this level of communication leads, or this communication between neurons to neurons actually leads to all our actions that we carry out every day. That includes your thought, hearing, speech, or movement. And what do we do as engineers or computer scientists? We basically place electrodes either on the scalp, that would be just beneath our head, or below that, below the skull, we place electrodes there to capture the electrical signals in the brain, which are then sent to a computer. So this computer, what it will do is that it will translate these signals into meaningful data, or say meaningful command through which we can carry out our intended task. For example, it can be used to control a computer or a device linked to a computer. So when uh, when the research started, it was started with the primary aim of improving the lifestyle or the quality of life of patients, especially suffering from neurodegenerative disorders such as amyotrophic sclerosis or paralysis or cerebral palsy and so on. So based on that, the BCI was used for different rehabilitative tasks. For example, you had your thought-controlled wheelchair, or upper limb prosthesis, as you can see from the two pictures here, or simply basically applying tetraplegic or hemiplegic patients to communicate with their care workers or the caregivers by spelling out what they mean to say. That is the cursor control. Or basically, it's the same thing. It's basically controlling the virtual keyboard and spelling out different forms of spelling out what they intend to say. But as the BCI research carried on, like since the advent of this millennium, BCI they started looking into the uh, everyday applications of BCI. So right now we have BCIs which can be used to play BCI systems which can be used to control or play a game, or even you can use BCIs to in a more immersive environment, or there are a lot of exoskeleton research going on which applies BCI, or in neuroeconomics or neuromarketing, where brain-computer interfacing is applied to understand the buying behavior or the say the preference behavior of uh, users. So there are basically, until now, there are few signals that have been that have been easily captured by both invasive and non-invasive kind of recording systems. The most common form of BCI, or most common form of application of BCI is movement imagination or movement execution. So just give me a minute. So what we have is the first form of signals that BCI is very good in predicting is your movement. It can be your left hand, for example, your left hand movement or your right hand movement. So the left hand, any form of movement actually originates in the primary motor cortex and the supplementary motor cortex. And in some patients, especially related to amyotrophic sclerosis-based patients, they can be more found in the parietal cortex. So they usually occur in the Rolandic they are dominant in the frequency range of 8 to 12 hertz and 16 to 24 hertz. But now in recent researches, we have also found that there is some activity in the above 30 hertz also. So movement can be of two types or multiple types. So you can have your left hand movement or your right hand movement. So your left hand movement and your right hand movement, there is a peculiar behavior that when your left hand, when you are trying to move or imagining moving your left hand, then the opposite side of your brain will be activated. That would be your right side of the brain. And when you imagine moving your right hand movement, then your left hand side of the brain will be activated. So this is one of the recognizable markers that we look for when we do a movement-based experiment. And if we look at the signal level, then you can see that just after the planning phase, that is after the participant or the patient have completed the planning of their movement, there is a drop in the signal. There is a drop in the signal power. So that call it as event-related desynchronization. And then from this drop again, there is a sudden rise, which we call as event-related synchronization. So basically, this indicates that when the participant or when the patient begins the activity, it can be your execution activity or your motor imagination activity. Then there is desynchronization in the neurons or in the dipoles or in the dipoles. So, and that's why basically we see this desynchronization or a decrease in the power. But when the on completion of the movement or movement imagination, then we can see that and the neurons, they again synchronize, the movement again synchronizes with each other, and that's why we have this sudden peak in the power. So this is another identifying factor by which we are certain that, okay, yes, so we are obtaining movement related signals, correct amount of movement related signals directly from the brain. So folks, so this is motor imagery or movement related imagination. Now we prefer participants to imagine their movement instead of executing the movement, that is physically move their limbs, because the EEG, the electroencephalography signals are often are very much affected by movement. I'm sorry, there's some sort of echo going on. Someone's mic is on, I guess. The next form of signal that I'm going to talk about is P300 based signals, and these P300 based signals are widely used for any form of recognition based tasks. And this is widely adapted by companies who are working in neuromarketing or neuroeconomics when we try to understand the behavior of choice by participants. So basically what happens is that when we see something or when we sense something of interest to the participant, that would be of interest to us as a participant, then there's the sudden peak in your EEG that's called the P300 signal. So as you can see from my mouse pointer, that this is the peak that I'm talking about. So this sudden peak occurs when something of interest happens to us. And if it does not happen, then basically it's similar to the red line, which is basically it's simple enough. It's just that we don't pay much attention to that form of signal. So now let's take an example where we are scrolling through different pages or different products in our Amazon store. And then suddenly we see an item that is of interest to us. So when we see that item of interest, then this form of peak would generate if someone in your lab or someone from my lab is capturing your EEG signals or your brain signals, then we would get this form of peak after at around 300 milliseconds after you have seen this particular item of interest. And this gives us an information that, yeah, okay, this product might be of interest to this person, so let's develop a recommendation system of similar items and send it and give recommendation to this particular user. So it's very similar to our clicking behavior, like based on our clicks, based on our clicks, any retail or any retail based online stores, they understand which would be which items would be of our interest, and then they keep on sending us different types of suggestions. So there are two forms. One is your buying behavior and one is your viewing behavior. So both these behaviors can easily be monitored by in this by your neural signals as well as your behavioral signals. The other form is steady state visual evoked potential. So this is a very specialized form of BCI signal where different stimulus is being provided to the user at different frequencies. And when we see, again, the behavior is quite similar to the P300 behavior. So when we see something of interest, then basically we can observe a similar level of frequency in our brain signals, and then we understand that okay, this is the item of interest for this person. So this usually generates in the occipital lobe. Because why the occipital lobe? Because the occipital lobe is directly it's connected to our is connected to our visual sensory organs, and that's why all information is transferred to the occipital lobe for further processing in the brain. And now, any form of, like we talked about motor imagery signals or P300 signals or your SSBP signals. So these are all, if you think about it in a control system perspective, then they're all open loop systems. Like you send you generate those signals, you evoke or you induce those signals, and then you send the control command. But no systems is perfect, and there might be chance that because we are using a computer to understand to extract the meaning of the signals, there might be errors in between the processing. So when these errors generate, then until now there was no mechanism to correct those errors. But what happened, like again, 20 years back, researchers found this error-related potentials. So this error-related potential is a very interesting signal. So this is an evoked potential, that is, it automatically generates in our brain without us even thinking about it. So this generates when the user is aware about something erroneous or some sort of error going on in the environment. So when the user observes an error or observes themselves committing an error, then this form of erroneous response is elicited in the anterior cingulate cortex of the brain. That's quite deeper in the frontal lobe. And through this signal, we can close the control system. So basically, we can have a switching device which says that, okay, whether the particular signal was erroneous or not. And if an error response was generated by the user, then we can just cut off the forward loop and ask the participant or the patient to redo the experiment. So in this way, we are also, in our neurorehabilitation exercise, we are also actually incorporating a safety mechanism. So as I told you, the ARP is basically elicited when we have a choice reaction task or a feedback-based task or a observation task. So a choice reaction task is like we are given binary choices, a yes or no or multiple choices, and then after we feed our response, we realize that the response was wrong. So those kind of responses are also erroneous response, and or you can say we call this the gut feeling of the user. And basically at those moments, the error-related potentials are generated in the brain. So I until now I talked about what are the different or the most common forms of BCIs that we work on, and basically how we capture different forms of signals to do different levels of task. But what happens in the what happens inside the BCI system? So inside the BCI system, So this is inside the BCI system, the three top, that is feature extraction and feature translation occurs. So we capture the brain signals and then we extract relevant features for the activities that the particular user is supposed to do. So, each, like as I told you as I showed you like few slides back, that each different form of activity um gives us or tells us a different story or a different form of signal. So we know that when there is movement, then event-related resynchronization and synchronization occurs. When there is something related to any target-related tasks, a P300 signal occurs, generates, or a SSBP signal generates, depending on the type of stimulus that we are providing. And then finally, if there is some kind of erroneous response going on in the environment or within our system, then the error-related potential occurs. So what the feature extraction box does, or the feature extraction step does, is that try to get those characteristics, those signifying characteristics from your raw EEG signals. Because when we see the EEG signal in the rawest form, we cannot really make sense of what that signal is trying to tell us. So we have to work on that signal. We need to develop the different forms of signal processing techniques. We need to we need to filter the signal in the right manner. Our approach needs to be in the right direction so that we can train our system to collect or extract particular sets of our specific sets of EEG signal. But currently, after the advent of deep learning systems, we can forego this feature extraction step and then move ahead and just go into feature translation, because uh, a lot of deep learning architectures actually provides us with end-to-end system of um, classification. So feature translation is nothing but it's basically your classification. So a classification, it could be a classification between your left hand and your right hand movement. It could be a classification between your targets and your non-targets, or it could be a classification between whether your signal was an erroneous response, or whether you had elicited an erroneous response, or whether it was a correct response. So the different so basically we just generate these control signals, and they can be used to replace, improve, restore, enhance, supplement, or basically increase our research knowledge for a particular form of experiment. So I have been talking only about electroencephalography because or EEG signals, because that's the most common form of BCI. Why? Because it's portable, it's cheaper, and there is a huge amount of literature on EEG. That's why researchers prefer to apply or use EEG signals. But there are different forms of recording systems where some of them are invasive, like we implant neurosurgery directly into the brain, or say into the cortex region of the brain. And then there is ECOG, or electrocorticography, where we implant the electrodes just over the cortex, beneath our skull. And there are other non-invasive techniques like magnetoencephalography. And how it is different from EEG. Magnetoencephalography actually looks into captures the magnetic behavior of the blood flow occurring in the brain during different activities, whereas EEG only works on the electrical signals generated by the neurons. And then there is a fMRI, which again maps the brain activity based on the oxygenation and the deoxygenation level occurring in the brain. So that's a brief introduction to brain-computer interfacing. It's a huge topic, so I just tried to cover it within like 15 to 20 minutes. And then now, what is collaborative BCI? So before moving into collaborative BCI, we need to understand how can we implement BCI in the decision making. So we know, we make decisions every second of our life. Right now, you might be deciding whether you're finding this presentation interesting or boring, or there are more high-stake decisions like that is taken by the government or some higher level organization like some big stock markets, whether to invest in a particular company or not, or whether a government should or whether the government should go ahead with a particular policy or not. Even critical decision making that takes place within the military, whether to take action or react to a particular situation or not. So an individual decision accuracy, basically, we have seen through literature that decision accuracy degrades because of limited processing time. So limited processing time means that we do not have sometimes critical decision making, we need to make decisions in split seconds, like within 1 second or 2 seconds of decision. And so we do not really get time to sit down and think about it. Then your decision accuracy degrades because of the quantity and the complexity of data. So and also the irrelevant information. So the second and the third point are quite similar to each other. It's basically, if you are fed with a lot of data or the data is very complex, then obviously it would take us a huge amount of time to understand the data and make decisions. So the data that must be transmitted to decision makers, they must be transmitted in a easily readable manner. But in most situations, that does not happen. And in those cases, our decision accuracy uh, decreases. And all these factors actually leads to poor decision making in high stakes and time pressured situation. There are other factors, and those are the mental factors that may affect the operators, your fatigue. Obviously, when you are sitting in front of you're in a meeting for hours and hours, or sitting in front of the computer trying to make sense of the information that has been laid out in front of you and trying to give out decisions or give out your analysis, then obviously your brain will be fatigued, or you may lose alertness, your attention level, and also the amount of mental workload that is done. So basically, your mental state is also directly correlated to the accuracy of the decision that you make. So that's about individual decision making, but you see that most important decisions in the world are taken by groups. And why groups? Because groups have this capability, it's called wisdom of a crowd, and groups have this capability of augmenting your action capabilities. That is, your members of a group can join forces to do something or to decide on something that is beyond the strength or endurance of a single individual. Or increased sensing capabilities, that is, a group has a higher probability of finding resources and noticing danger. And then there is an increased cognition and intelligence obviously found out in groups. So we can now say that yeah, so that's perfect. So group decision works best. Instead of individual decision making, we can all go ahead and make group decisions. But again, there are disadvantages to that too. I mean, so what happens in a power of crowd is, obviously we get augmented wisdom when we decide in a group. But in every group, there is always a leader, and this leader might be overconfident. So, which is something we call as overconfidence biases. And the other group members, they tend to follow the leader, and even if they have doubt on the leader's decision, they will follow the leader's decision. So as you can see in this cartoon, that the leader said yes, I, or I, which is quite famous in which is in Northern Ireland we say I instead of yes. And the other, even if the other group members, they don't agree with his decision, but they are still respond as yes. Then again, groups, due to time constraints, your group decision making can again fail. So that really does not solve the problem that we faced in individual decision making. And sometimes sometimes the members are not motivated enough, or some members, even if they are good decision makers, they are not confident in their decision. They suffer from they might suffer from, say, imposter syndrome, and that's why they don't want to be forceful in their decision. So this is where the neural signal comes in, because even when we have observed in the signals, and even when even through literature, we found that even if you make a wrong decision, the brain uh, the brain makes the correct decision for you, or the brain indicates whether your decision is correct or not. So that's basically what we call the correctness of the decision. So obviously, it's that split second decision that can be captured in the brain before your uh, decision is overwhelmed by other factors, such as, say, an overconfident member making a decision, and or you're underconfident, or some other things. So basically, it is that split second decision that we try to capture in our research to uh, to assist the individual to move towards the correct decisions. So that's where basically brain computer interfacing and groups come in, and it forms collaborative BCIs. So the disadvantages of BCIs is that it has low accuracy and low speed, whereas groups have the disadvantages that it has leadership bias and it has like time constraints. But when we bring the two together, and when we form collaborative BCIs, then these disadvantages are mitigated. And I'll show you in my results how it is done. But before that, so our collaborative BCI framework is quite simple. So say in this example, we have two users who are responding to a particular situation. So through their mouse clicks, they are sending out their responses. But we are also capturing their behavioral data in the form of reported confidence, and we are capturing their EEG. And after applying our EEG algorithm to translate the information, we the here the information translation is the confidence of the particular user on the decision. So say I made a decision of yes. So what is my confidence for for my decision of yes? So if it's over 0.5, then we can say okay, or if it's say over zero point 0.7, then we can say that yes, he's confident in his decision. If it's less than 0.4 or zero point 0.3, then we can say that he has made a decision, but he is not confident about it. And a similar response can be gained, say, somewhere in between, where we can say that this person again gave a response, but he is neutral about it. He does not have low confidence or high confidence on that decision. So we then weigh these confidences with their decision, and then we sum them up for each users, and then we form a group decision. So basically, the confidences here acts as a weight to the decisions of each user. So the data recording and processing takes place in the following form. So we have your EG data, then we apply different forms of filtering to perform correction, including ocular artifact correction, and then we also apply baseline information. And we obviously work our signal of interest out of two forms. When the person saw the stimulus, so what happens after, say, 1 seconds after he saw that stimulus, what happens within that range, and then and during the response, like when the person has made his decision and clicked on the mouse or any other device, then what happened what took place in the brain, what kind of activity took place in the brain, say 1 second before the response, so that this person could reach this particular response. So the confidence estimation is done in this form, in this way. So as I told you, that we are basically gathering the decision confidence of the correctness of the decision of the user. So from a machine learning perspective, we have binarized our labels. So for any correct decisions, we have labeled them as -1, and for any incorrect decision, we have labeled them as +1. And we apply different forms of classifiers like least angle regression, logistic regression, and random forest. And then we found that random forest actually gave us the best results. And how did we simulate groups? In our case, say we had 10 participants who took part in this experiment, and then we developed combinations of these participants for different group sizes. So for example, we had participants where the group size was 1. We had participants where the group sizes were 2s, that is the group size of pairs. And then we had participants where the group sizes were 3. So there were different combinations of the group sizes. And then we aggregated these individual opinions to form the final vote or the final decision. So the traditional way of aggregating our individual opinion is the majority form, and that's what we compared against. This is the traditional and the standard way. So each decisions were made by the users, and then we just weighted their responses and found the group decision. And then there was this confidence-based groups where, along with the decision, we also asked the users to report their confidence, which we call as subjective confidence. And then again, we weighted the responses and then found a group decision. And then this is our BCI assisted groups where the decisions were made by the users, but we asked the BCI, but instead of asking the participants to record their confidences, we got their confidences directly from their BCI, from the neural signals. And then again, we used a weighted majority to reach a group decision. So So basically, we carried out our methodology in various experiments. So we started off with a simple matching experiment, followed by a traditional visual search experiment, and then we also started going into more realistic environments such as speech perception or facial recognition from surveillance applications. That is, we are getting multi-view. Each user is seeing a different view of a particular surveillance, and then we are collating the decisions of those users, and then target detection while in a video feed. So as you can see, from 2014 and onwards, we are still working on it. We have moved from a controlled environment to more and more realistic environment. So our final aim is obviously to get this collaborative BCI out of the lab and deploy them in real-world scenarios. So this is an example of a realistic visual search experiment where the participants basically, so the participants had to detect whether the picture, a particular picture had a polar bear amongst the penguins or not. So the experiments were designed in this manner, like you have the fixation cross, and then for say 1 second, and then the stimulus was shown for 250 milliseconds, and then the stimulus was masked for 250 seconds, and then we asked the users to respond. So this is an example of how of of the different types of pictures. This is just one example, and you can see that there is a small polar bear there amongst the penguins, and basically you can understand that it's a very difficult task to complete within 250 milliseconds because it's just a hit and miss or just see and go kind of experiment. So, but what we saw was that our BCI, our brain computer interfacing, worked much better than this majority. But here we use the logistic regression classifier. And when we asked the participants to report their degree of confidence, then we found that obviously when we are weighting the decisions alongside when we are weighting the decisions, then it is working better for groups of 2, for even number of groups, 6 or 8. They work much better than the majority, but they are almost at par for the odd number of groups. So from here we can see that a weighted form of decision making is very useful in tiebreakers actually. But when we implement our BCI, when we compare our BCI with both the reported confidence and the majority, then you can see that the it's far better. It's much better than the other two standard methods of majority and reported confidence, especially for the even size groups. It means that BCIs, brain computer interfacings, are actually much better tiebreaker than the other standard methods. So this is another experiment where we showed where we had a soldier, where we generated a dynamic environment, and basically we took the participants took the role of a soldier who was walking along a corridor with multiple doorways, and the task was to decide whether the character appearing was wearing a helmet or a cap. So this kind of simulated the behavior of whether one of the character was an enemy or a friendly person. So this is an example of how. That's weird. I cannot run the experiment here. Give me a minute. Okay, so this is the experiment. And you'll see that different characters are appearing in screen, and this is what actually 250 milliseconds look like. So this was what is actually shown to the participants, and then the participant has to respond what the participant has seen, whether the person was wearing a helmet or a cap. So the decisions were taken using mouse clicks, that is right mouse click when the decision was a cap, and left mouse click when the decision was a helmet. So this is what the brain signals look like, and you can see this is what the brain signals look like, and we can see that in the response locked signals, the correct decisions, when the participants made the correct decisions, then it had much higher amplitude as compared to the incorrect signals. And this is what we termed as decision-related potential. And this basically indicates that the participant tends to make higher confidence, tends to have higher confidence when they are reporting a correct response instead of an incorrect response. And when we look at the accuracy, you can obviously see that any form of BCI actually works much better than the traditional majority or confidence majority. And mostly you can see that the green and the purple line, which is when we are developing the BCI based on EEG confidence and EEG response time and confidence. So the other form of experiment that we did was an outdoor experiment where we simulated an environment where the participant uses night vision to see a person walking towards the outpost. And again, the task was to decide whether the person is wearing a helmet or a cap. And then they had to provide a confidence estimation after the decision and the rewards and penalties. And here we incorporate a reward and penalty system where as the character comes closer to the outpost, you will be getting less reward. So we simulated a situation of time pressure in this case. So again, so this is how it looks like, and you can see this is how the experiment. This is what you can see, like this person is walking towards the outpost, and as it goes closer, your reward is also reduces. So again, we checked the response locked epochs and we found a similar form of response behavior. Like the correct responses have higher confidence than the lower responses, the incorrect responses. And again, we got a similar result and we proved that basically CBC, our collaborative brain-computer interfacing improves the group decisions under time pressure conditions and when there is also when there is no clear onset of a stimulus. So right now what we are working on is basically combining AI decisions made by an AI with humans. So that's what we are calling AI human teaming. So we have a group of humans and a group of agents or artificial intelligence agents or virtual humans as we call them, and they come together to make a decision together. So right now that's what we are working on. And also we are basically training the AI to mimic human-like behavior so that the trustiness of the humans towards the virtual humans would increase. And until now, we have been only working on binary decision making, but slowly and slowly we are moving towards non-binary decision making also. And right now we are just applying, we have only been using a form of video environments, but now we'll tend to move towards multisensory environments, which would include video, audio, and even vibrotactile kind of situation. And then the next form of experiment that we will do is obviously have BCIs based on group selection, where each members of the group right now, each members of the group were carried out their task in isolation, but slowly and slowly we will start incorporating experiments where where the users or the participants are communicating with each other to reach a decision. So that's all, folks. And this is my email ID. We always look for PhD students. So if anybody of you are interested to apply for a PhD scholarship, then do let us know, and we are very much willing to get more and more students and work on different forms of brain-computer interfacing or artificial intelligence or machine learning based work. So thank you everyone for your time and for listening. Yeah, that's it.
Thank you, Dr. Bhattacharya, for your fantastic lecture. And if anyone having any question, they can ask.
Yeah, hi. I have one question for you. So I
Yeah.
was just, you have applied machine learning in most of your work. So can I just ask something? Are you looking forward to, I mean, like applying deep learning as well? Because I believe that deep learning would give much, I would say, yeah, I can definitely say better results than random forest, I believe, because random forest has a lot of problems.
Yeah, for offline based analysis, we are obviously going for, we will obviously look into deep learning, and you are right, like deep learning gives us much better result. But you see, these experiments were designed specifically for a particular user group. In this case, they were designed for military personnels, and so these needed to be deployed for online level tasks. So we needed something that could respond to these signals really fast, and that's why we had used random forest. But yes, deep learning works well. Yes.
Yes, because why I'm saying this is because random forest is definitely very fast to train. There is no doubt about that. But in deep learning also we have the concept of transfer learning now, right? So you do not really need a lot of data to train as well. So I think even that would give you a faster result. I
Yeah,
think
that's
that
true.
can
I
be.
mean, right now deep learning is like I mean, it has moved classification problems into a different dimension, and yeah,
Yes, yes, yes.
we do use deep learning in our offline based analysis or offline based results. These were just the results that we had reported
Okay.
to our stakeholders. All right. Yeah, but people do really usually, but my researchers actually apply deep learning based transformers based. They have started using transformer based
Yeah.
algorithms
Okay.
for
Yeah.
this kind of tasks. Yes.
Yeah. Attention is all you need. So yeah, transformers
Yeah.
is the thing of the day. Yeah. Okay. Thank you.
Yeah.
Thank you. Thank you very much.
Yeah. Yeah. Just to add to that, we are also trying to implement it on a more edge based scenario, and that's why we have started off with classical machine learning rather than applying deep learning straight ahead.
Uh, yes. Okay. Okay. Fine. We can probably talk about it later. I think I would.
Yeah.
I have like a lot of questions, so I think that would take a lot of time. So yeah. Thank
Yeah,
you. Thank
sure.
you.
You can obviously email me, and we can have a
Yeah.
discussion then.
Okay. Okay. Yeah. Thank you. Thank you.
Any other questions? I have one question, Saugat, and I think for these BCI related applications, I mean, the computations must be very fast. So what type of computational platform you used to process the data?
Yeah, right now we have used our simple. That's why we need we that's actually follows on along with my next question, last question. But we had a very high performance computing device along with us. A very high performance computers that that took care of the processing, and we could get the processing. We could get the. I did not show that the particular result, but we could get the results under 1 second.
But in some cases, I mean, that those devices should be portable, right? I mean, it may not be some.
Yeah, that's it's a basically, you see, it's a very new area, and we first need to understand what's happening in the brain before moving into deployment phase, and that's where we would look into, and that is actually one of the tasks that we would be doing in the future. Actually, that would be deploying these algorithms for real world scenario where we need a faster processing time. So that's basically that's one of the I'm writing a grant on that and hopefully I might get a grant. Or if I get the funding, then it'll be this work will move to in that direction.
Okay. Okay.
Laura,
And
sir,
one.
there are a few questions in the chat box. Some
Yeah.
of us have
Sorry.
put a question in the chat box.
Okay. Let me see.
Yeah, I can see the questions. So the first question was, this could be useful in defense combat. Yes, actually, the last two experiments that I showed you, the corridor experiment and the outpost experiment, they were funded by the UK Ministry of Defense. And we have actually handed over all of our codes and all of our results to them, and they are carrying out, they are taking it forward. Is there a follow-up question to that? Okay. The next question is it is possible to decode thoughts with this? I don't understand what you mean by thoughts, but if you're thinking about more abstract form of thought level, then it's still a very new. It's like we are going. We have been taking baby steps all in this research, like brain-computer interfacing research. An abstract level of thoughts would be something that would come up in the next 5 to 10 years. But I have colleagues in University of Essex who have been working on semantic reasoning, and basically they have been moved. So this is our baby step forward towards more abstract level of thoughts. I hope this was the question that you had asked, Julius. Is there any other question?
Okay, if you have more questions, I mean, I think you can we can talk offline also. Saugat already shared his email also. I mean, if you have any further query, we can communicate with him, right?
Yeah, of course, I'm open for collaboration. Yeah.
And just let me play one video. I mean, which should be played the first of these before starting this lecture. Just a minute. This is just an introductory video of our university.
All right.
Can you see my screen?
Yeah.
Thank you, Saugat, for connecting with us. Let me make the concluding remarks. All the guests and all participants, BTech, MTech, MSc, and PhD, and faculties of ITER, I would like to thank you on behalf of the organizer. It is indeed my pleasure to make a few closing remarks and express gratitude to the speaker, participants, and organizers. And obviously, we able to understand so many things about the ML application on BCI. And if we set up any BCI lab, I think you can get some help from you, right, Saugat? And right?
Yeah, definitely. Yeah, definitely.
And if anyone, any master students interested for the PhD on this topic, and he can apply for this.
Yeah, so we have this competition, like a PhD competition I think it's out every January, the advertisement. So obviously the students needs to contact me or some other researcher first, and
Okay.
then go through the application process. Yes. So they are directly, it's a competition, and they are directly funded by our Department of Economics.
Okay. Okay. Thank you. Thank you, all of you. So I'm going to close this meeting now.
Okay, thank you, Rodolph.